All right, good morning, everybody. Hope everybody had a good weekend, and week is off to a good start, even though we're halfway through it already. Right? At the end of the day, we will be halfway through the week. So, today we're going to talk a lot about the Nobel Prize that was recently announced last week, right? It's been a week since the Nobel Prize was announced. We talked a little bit about it last week, but we're going to do a little bit of an activity. I want you to understand why they won the Nobel Prize. What was so important about what they were doing that deemed them for the Nobel Prize. So what we're going to do is we're going to do a little exercise. I'm going to hand out, not to everybody, but to you all work in some small groups. I'm going to hand out some pieces. How many people have played with model kits before? Okay, a few of you, all right? So this is not the model kit you grew up with, okay, but it's similar. And so what we have here is a carbon atom. Everybody will get one carbon atom, or not everybody, but each group will get one carbon atom. What can you tell me about carbon when you look at that model? What do we know about carbon? Carbon likes to form 4 bonds. What else do we know about carbon? What about the bond angles that you see here? They're tetrahedral. That's right. So it forms the shape of a tetrahedron. If you were to draw faces, you would actually draw what's known as a tetrahedron. Does anybody know what the bond angles are on a tetrahedron, approximately? About 109.4, right? So around 109 degrees. Of course, bonds in real life wiggle a little bit, so we're always looking at kind of the average bond angle, right? The models that we have, are they great models? Are these really good models for an atom? They're about as good as we can do, right, and physically, but they're very rigid. But in reality, bonds will wiggle and move and shake and all kinds of things. And so it's actually best to model atoms in a computer where they can actually be a little more realistic. But nonetheless, we're going to use these. Is all carbon tetrahedrally shaped? No. There's actually different types of carbon, right? This is what we would call an sp3 hybridized carbon. For those of you who haven't had organic chemistry yet, I'm talking about a lot of things that maybe you do, maybe you don't know, and that's okay. But carbon can actually form different shapes through what's known as hybridization. But we're going to use what's known as an sp3 hybridized carbon today. Okay? And then I'm going to give each and every one of you a different, 4 different colored sticks. And you are going to attach those sticks to your carbon atom. And so the way that you do that is you will simply take it and you'll push it on there till you hear it snap. Okay, so you'll hear it snap a little bit. When you pull it apart, it will make a popping sound as well. But when you hear that snap, you've got it on there good and tight. Now, what we're going to do is I want everybody just to attach the 4 different colored sticks on the carbon at random. Okay, so I think what we're going to do is we'll have you all be a group. I'm going to ask you to be in that row. That back row will be a group, and then this side thing will be a group. Okay, so let me pass out carbon atoms first. Carbon atoms. They all can get together. Come in handy to have it. So, pass these out, but hold on. We'll figure it out.
Why does yours not want to go down? It's fine. It took me when I did.
All right, so what I want you all to do is I want you all to attach your 4 colors to your 1 carbon atom. Okay? Now you'll want to grab the carbon atom kind of like this as you push the piece on, or you might make it come apart. You can't break, well you can, but probably you can't break it. It's pretty rigid. Now I want somebody from every group, I want one person to get out a piece of paper. I want everybody's name on that piece of paper that's in your group. Please print the name and put the ID number because it's going to be your attendance rating day. So showing up to class does matter. Print the name and then write out your ID number to the side in case I can't read your handwriting. And somebody's going to be what we call the scribe. Somebody is going to record what you're discussing on that piece of paper. Okay? Not yet, not yet, not yet. No, we're not doing that. So you just have to decide. Somebody has to be the scribe. Okay, now, it's important to know what scribes do. I have had to be a scribe many times when I went to the National Science Foundation. But every year I go to the National Science Foundation and I work reviewing proposals. We give out millions of dollars to people to do research. And when you're reviewing a proposal, there's a panel of people that are reviewing, and there's somebody who is scribing, who's recording kind of the minutes, if you will, of the discussion. So, what I want each of your groups to do is to discuss, did we all make the same thing? Did we all make the same thing? Okay? And you have a discussion amongst yourself, did all the groups actually make the same thing? And the scribe will take some notes of that discussion. I'm going to give you about 5 minutes to have that discussion. So get together in your small group, introduce yourselves to one another, and answer the question, do you all believe we made the same thing? There is no right, well, there is a right or wrong answer, but you won't be graded on a right or wrong answer. You can join that one.
Unless we're talking about your I guess we could go Does that not make them a different thing when they're put on their different groups?
No, I just don't know why.
I forgot the word for it, but I literally just had it. There's like
switch blue yellow. Technically, it's going in the same order, just going in the opposite direction.
So can we make the same molecules that one without
These two.
So is it
That one is
if we could see them? So is that our answer? Because I'm trying to think of
Yeah.
Can we see theirs?
Not yet. You cannot see theirs yet. You have to, right now it's just a mental exercise, but you will get to see them in just a moment.
I still go no because I.
There is a method to the method. There is a method to the madness.
So it shouldn't, it doesn't come from.
Okay, has the scribe had a chance to write down what you think it is and a brief reasoning?
Not yet. We're getting there.
Okay, I'll give you another minute.
So in theory, because others is in the same word, so we have like chlorine, bromine, iodine, and then like that's probably not gonna happen.
Okay, wrap up the scribe on the first part of the exercise. About 30 seconds. Okay, what was the question? Are they the same? So we have a question. And we might form a hypothesis that says something along the lines of, yeah, we all made the same thing, or no, we didn't make the same thing. How many think we made the same thing? How many think we made something different? Okay, about 50-50 of it. Okay? When we look at this, we all will agree that we have a single carbon atom with the same 4 different colors attached around that carbon atom, right? So if I was to name this, I would name this yellow, red, black, blue, methane. Don't worry about how I came up with that name, okay? And we'd all have the same name. So it should be the same, right? How can I test that hypothesis? What were you all wanting to do? You were wanting to look at everybody else's. So this is we have a testable hypothesis before us. So now, do I look at somebody else's model? How will I interrogate whether or not I have the same thing? How will I test it? I can try to switch the groups around, okay? What else can I do?
You can try different ways and see if it's the same.
I can, that's true. What else can I do? I can physically take my model and compare it to everybody else's model. If it's the same, what should be the result?
The colors are in the same place.
They're all in the same places, and if they're not the same, we'll have colors that aren't in the same place, right? All right, so let's test this hypothesis. So, we're going to start with this one. Now, if this is true, I should be able to line them up. I've lined up my carbons. The blue sticks line up, the yellow sticks line up, but look, the red and the black don't line up. Are these the same? They are not. So, somebody keep score for me. We have one group that is not the same. Look at group 2. Aha! Look at group 2. All 4 colors line up. Is this the same or different? Same. So we got one not the same, one the same. Let's look at this one. See what we got here. Not the same. No matter how I turn that around, I'm never going to get any more than these things to line up, right? So another one not the same. Not the same, right? Now it turns out that if we had a big enough class, when I usually teach organic, we got about 150 to 180 students. Everybody brings their model kit, everybody builds this. And I go around and I do this, and it turns out to be 50-50. We were pretty close, right? But we had such a small group, okay? So, how are these molecules that are not the same related to one another? I've got a single carbon atom with the same 4 things on it. How is this and this, which we all agree are not the same, how are they related?
Composed with carbon stuff.
They are composed of the same stuff. If this was a real molecule, they would have the same molecular formula, for example.
But they have a different structure.
They have a different structure in what respect? I've got the same stuff connected to everything.
How is
They're all tetrahedral.
how is
How it's connected in 3 dimensions is different, right? And what you'll notice, if I set these 2 down, now how are they related to one another? They're mirror images of one another, right? There's a mirror plane here. So this is like you standing at the mirror in the morning and seeing your mirror reflection. In the morning when you stand up in the mirror and you raise your right hand, what does it look like is actually being raised? Your left. That's what we have here. Now wait a second. These were not the same. Were we the same? We were the same, right? Can I have a mirror image of that? Let's see. I don't think we are the same. Yes, we are the same. That's not a mirror image, is it? When we have a molecule that is a mirror image and is yet not superimposable, everything has a mirror image in a way, right? I can put this up in a mirror and I'll get a mirror image. But when I have what are called non-superimposable mirror images, I have what are known as enantiomers. Okay, don't worry about that terminology too much yet. You'll learn about it when you get into organic. But this carbon is special. It's called a stereogenic center. Okay, stereochemistry, things in 3 dimensions. All right. Now, how can they make it identical to me? What would they need to rearrange? Pardon? The states, okay, so a little more. Switch any 2 groups. So somebody in this group, just take 2 sticks and swap them. Doesn't matter which 2 colors. So she's swapping the position of the blue and the black. And what do we have now? The identical thing. Okay? Anytime you have a single carbon atom, actually you can have more than 1 carbon atom, but let's keep it simple. Anytime you have a single carbon atom that has 4 different things attached to it, you have what's called a stereogenic center. Okay? Now, when you all put this together, was it easy or hard? It's pretty easy, right? You just snap things together. Pretty easy. Now, if I told you to make identically what I have, would that be easier or harder? Why would it be harder?
The first time it was random.
First time was random, very good. And then the second time, if I told you to make identically to what I have, what do you have to do? Got to think a little bit more, right? You got to think in 3 dimensions. You got to think about how this particular group is oriented 3-dimensional, right? You can't just put them together at random. Okay? This is a general area that is very near and dear to my heart. It is called chirality. You all had a reading assignment from the chemistry book on chirality, right? This is an interesting topic for a variety of reasons, but the most important reason from your perspective is, and I've told you this before, structure is equal to function. Okay? What else that you can think of might be chiral? Doesn't have to be a carbon atom of 4 different things. What other things in real life that you would have experience with each and every day are chiral? When you read that, what does chirality mean? It's Greek for what? Handedness. Think about your hands. Is your right hand the same as your left hand? Can I superimpose my right hand onto my left hand? Nope. But they are mirror images of one another. Right? Your hands are chiral. So when you all get into upper level chemistry courses, they will talk about molecules that have chirality or handedness. There will be right-handed molecules and there will be left-handed molecules. Right-handed? Well, it's right-handed now. And then somebody else's was the left-handed molecule, right? Non-superimposable mirror images of one another. What else in real life might be chiral?
Your feet.
Your feet certainly are chiral. Your cup holder in your car. Maybe. I'd have to look at that one. Would your coffee mug be chiral? If I took 2 coffee mugs, I think you all would agree, and let's assume there's no writing on it, all right? So 2 plain old coffee mugs, you can set them one here and one here, you need to have a mirror plane, but I can actually superimpose one on the other. In reality, it's hard because I can't smash the coffee cup, but you would see what I'm saying, right? Coffee cups are not chiral. How many people like to ride on boats? Anybody? What on a boat is chiral? Not the steering wheel. No, the steering wheel would be round, and if I take it and its mirror image, it would be superimposable. What drives a boat? A propeller. When you look at propellers, you have right-handed propellers and you have left-handed propellers. Have you ever seen a pinwheel? A little kid's toy? They are chiral. Screws are chiral. You can have a right-handed screw that you would turn to the right, but you can also have a left-handed screw that you have to turn to the left to get it to go in. Okay, so they call those reverse thread, but they are mirror images of the other. They are chiral.
What about like golf clubs?
Golf clubs, let's see. So if I'm thinking about a golf club,
Like the
because
way-
they got a twist in them usually, right? I think they might be chiral. Can you have right-handed and left-handed golf clubs? Yes. Then I don't play golf, that's why. Okay, other than putt-putt. But, yeah, so they would probably be chiral.
Desk,
A desk?
like you know in high school, they have like the right-handed desk.
Ah, very good, right? So this desk, chiral or not chiral?
Not chiral.
Not chiral. But in the high school where you had the desk that had the arm and then the piece, you did have right-handed and left-handed desks, right? They were mirror images of one another and they are chiral. How about a hammer?
No.
Have you, no, very good. Have you ever gone to the hardware store and said, where are the left-handed hammers? You never have. But what other tool do you use that they actually, and you may have experienced this when you were in kindergarten as an example, and you had to go buy left-handed scissors. Scissors are chiral. Okay? These things exist other than in molecules, okay? It's an important area. Why is it important? I want to use your golf club. Why is it important to have both right-handed and left-handed golf clubs? Why does it matter?
Because if you stand on the plane, I guess on different directions, I guess you're also a mirror image.
Okay. All right, very good. Very good start. It turns out it matters if you try to grab a left-handed golf club and do a right-handed swing, the head won't line up right? It just won't. Okay? If you put the wrong propeller on your boat and you push forward, you'll actually go backward. It kind of makes things difficult. Okay? Think about gloves, like a baseball glove. We make those right-handed and left-handed. Have you ever tried to stick a right hand into a left-handed glove? What happens?
The pinky going to the thumb.
Yeah, the pinky goes into the thumb and it doesn't line up and you try to cram, it just doesn't work. Okay? It turns out that the molecules in your body, your macromolecules, your proteins, your DNA, it's all chiral. And when you take something that's chiral and you interact it with something else that's chiral, you can have things that fit, and then you can have things that don't fit. Okay? Just like my right hand in my right-handed baseball glove will fit, my right hand in the left-handed baseball glove will not fit. And that sounds pretty simple, right, and straightforward, but think about it. If you take a drug that has a carbon atom, at least one, that has 4 different groups on it, and it has to interact with an enzyme, one image of the drug will fit into the enzyme and block it and shut down the process and help you relieve your pain. The other one will not. Does that have a consequence? At the very least, it means what? It means that if you take the wrong enantiomer, you won't have the therapeutic benefit. At worst, it could mean that it's toxic. So, how many people know about Aleve? The drug Aleve. Okay? Many of you have probably taken Aleve. It's called Naproxen sodium, right? Now, Aleve is a chiral molecule. Okay? And it turns out that if you read the back of the bottle of Aleve, it will say either, I can't remember which enantiomer it is, but it'll either say R or S naproxen. I think it's S naproxen. Okay? I believe it's S naproxen. Don't worry about S. S and R are kind of like right-handed and left-handed. Okay? It's just a nomenclature that you'll learn in organic chemistry. So it turns out that naproxen is the left-handed molecule that we want to take. That relieves your headache, your fever, all that stuff. If you were to take the other enantiomer of naproxen, it will destroy your liver. It is a liver toxin. It's a very potent liver toxin. So, when you go buy that bottle of Aleve, do you want to buy a bottle that was made at random where you had 50-50 of both? Why not?
But I want the chances.
That's right. One is going to cure my illness. The other one is going to kill me. That's not a good medicine, is it? And we just realized that it's very easy to randomly put things together. Turns out for chemists it's very easy too. I can go into the lab and make things what we call racemic, which is a 50-50 mixture of both enantiomers, which is what we were pretty close to making here. Right? So I can make those very, very easily. What's tough is making only the one mirror image that I absolutely need. And it matters. It matters. And it turns out that the Food and Drug Administration, if you make a chiral drug today, and most drugs are chiral, if you are going to administer it as a mixture of both mirror images, you have to prove that there is no harm done in doing so. How hard is that to prove? It's extremely difficult to prove. And expensive. To develop a drug today costs roughly $1 billion. Even a simple drug costs about $1 billion to develop, ish. Probably a little higher today than the last time I taught medicinal chemistry. Okay? So, let's think about that just a little bit. I'm a chemist. I've got flasks. I've got chemicals. How do I move atoms into 3 dimensions and control that stereochemistry? By putting things in a flask. Can I actually manipulate atoms one at a time? Can I go in and can I take a red stick, like I did here, in a flask and connect it? I cannot. right? You've been in chemistry lab, you know, we mix things together and they stir and then we may boil them. But we're not sitting there taking atom by atom and telling it where to go, right? We depend on reactivity. So somehow we have to control where the atoms go without us being able to take our hands and stick them exactly where we want them. That's why the Nobel Prize was so important. What did they come up with? They came up with catalysts, right? Let's see, let's do this. So they came up with catalysts that allowed for the atoms to be placed in 3 dimensions quite easily, okay? Now, the first reaction, you all don't need to know all of this, but this was what Dr. List first proposed back in early 2000. He used this as a catalyst. This is an amino acid. This is called proline. This is a natural molecule that exists in nature. Is it chiral?
No. Yes.
It is, actually. This is a carbon atom, right? Each one of these points is a carbon atom. That's a carbon atom. That's a carbon atom. That's a carbon atom. So we have a carbon atom that actually has 4 different things attached to it. It doesn't look like it, maybe, right? But it's actually connected to this group. It's connected to this, which is different than this. And so that's 3. But you need to know that in organic chemistry, we quite frequently don't show the hydrogen. So there's actually also a hydrogen attached to that molecule. This is chiral. It exists in nature as only one mirror image. That's actually a whole area of philosophical study. Why did nature make things chiral? We really don't know. Pardon? Oh, okay. This catalyst interacts with these molecules just like your hands interact with gloves. Right? So think about this. If I put you all on an assembly line at the Rollins baseball glove factory and they were making an equal mixture of right-handed and left-handed gloves, how would you separate them and put them into the correct box? I would use my right hand and go, that fits, that fits, that fits, right? And I would let the left-handed gloves go down to somebody else. But I could actually pull out all the right-handed gloves by having my right hand fit in the right glove. And that's what's happening here. We don't need to get into the mechanism. That's not important for this class. But this is chiral. These molecules then can interact with this chiral catalyst in a way that it allows for these atoms to be placed in 3 dimensions specifically. This carbon atom right here in the product is chiral. It's got this group, it's got this group, it's got this group, and then of course the hydrogen, which isn't shown. And that's very, very important. When you go back and look at the last good number of Nobel Prizes that have been awarded in chemistry over the last 3 or 4 decades, they have been awarded to organic chemists. Not always, but a good proportion of them have been awarded to organic chemists for being able to make things enantiomer pure, as we like to say. Okay? And it's important. It's important because from a medical point of view, from a biological point of view, from a materials point of view, there's a lot of reasons why you want to control structure, because again, structure is equal to function, right? And so both Ben List and Dave McMillan worked on this extensively to develop catalysts that can do this. This work has ended up being used by companies like Pfizer and Merck and Johnson & Johnson, and chemists can go in now and put atoms where they need to with the use of these catalysts. Do you have a question? Yeah.
So you said that before this, you had a 50-50 thing in your medicine. So is one of them, and you had to prove that it didn't affect you. So if you're taking like a medicine, is half of it
Toxic?
doesn't work?
So that's a good point. So it turns out, like I was talking about Naproxen, they sell it to you as sell it to you only the left-handed version. Ibuprofen, however, is also chiral, but you get it as a 50-50 mix. The reason is because the other enantiomer they have shown causes very little damage, if any. Okay? So it's easier to make it at random, put it all together, and give it to you. So what does that mean? When you take an 800 milligram ibuprofen, only 400 milligrams of the active ingredient is actually working. The other is just being excreted. Yeah?
Oh, see, when you first said it, I thought you were saying like the pill, either the pill is like,
Yeah.
but you're talking about half of the pill.
I thought, yeah, the way I took it was one of the pills was placebo.
No,
and the other wasn't.
Not a placebo. Not at all. No, the molecules that are in the pill, right, for naproxen sodium are just the left-handed version. No matter which pill you look at, okay? Yes, ma'am.
So what would be the difference between regular strength Tylenol?
I'm sorry, I'm having trouble hearing you. Can you take your...
What would be the difference between the regular strength Tylenol and the extra strength?
Okay, so it turns out that in Tylenol is not a chiral molecule. So when they talk about extra strength, they're just talking about you've got more Tylenol molecules in a dose. Okay? So, for example, we could say for ibuprofen, the 200 milligram tablet would be regular strength and the 800 milligram tablet would be extra strength. We could call it that. Tylenol just kind of branded the extra strength piece. Okay? But Tylenol is not chiral. And so it's easy to make. And it's easy to administer. You don't have to really worry too much about that. But oddly enough, this is a little off topic, but it's something that my wife studied when she was at Vanderbilt Medical. Well, she was a lab tech at Vanderbilt when I was a postdoc there, and she worked in the med school. They did a lot of studies on Tylenol. It turns out Tylenol is highly toxic, believe it or not. In Europe, Tylenol is known as a suicide drug, actually. The amount of drug that you take is actually pretty close to the toxic level. There are actually many cases in the United States every year of Tylenol overdose, accidental overdose. So, don't just take a bunch of Tylenol, okay? It actually is a pretty toxic thing. And yet, we put it over the counter and let people take it. Largely for historical reasons, because Tylenol is so old. Okay? All right. So, pretty important stuff, right? Being able to control the stereochemistry of a reaction. Yes?
What about aspirin?
Aspirin, acetylsalicylic acid is not chiral. It is not. It does not have a carbon atom of 4 different things attached to it. Yeah.
What's the difference between all these different brands?
Different brands?
I'm saying like aspirin, ibuprofen, Advil, Tylenol. Like, what's the difference if they all like do the same thing?
They have the same effect in terms of if you have a headache, they cure your headache, but they don't work the same. Okay? We're getting a little off topic here. We're talking more medicinal chemistry than Nobel Prize. But aspirin works on a different enzyme than does naproxen or whatever other drug. So what those drugs target in your body is different. Okay? So there's actually a series of enzymes in your body that are called cyclooxygenases. What they do is they take fatty acids, particularly arachidonic acid, they oxidize it, cyclize it into these what are called prostaglandins, and prostaglandins are responsible for pain and other things. Prostaglandins are useful for a variety of things. But they can cause inflammation, they can cause pain, and so you take things that block those enzymes from functioning. Aspirin can do that, Tylenol can do that, but they will block at different places and they will have different targets, if you will. Okay? So that's the generic explanation. Kind of telling you some partial lies here, but I'm trying to keep this up. Yeah.
Okay, so shifting gears. In biochemistry, we like to use enzymes to do the catalysis, right?
Yep.
They're there. Is it cheaper and easier to manufacture these catalysts versus finding an enzyme that does what you want it to? What,
Yeah, so my group, I'll talk about my research later on, but I'll just give you a little bit of a hint. My group is what we call a bioorganic group, and we actually do use enzymes to do not biochemistry, but to do organic chemistry. We use an enzyme from the pig liver called pig liver esterase. It's cheap, readily available. It can take a molecule that's not chiral and make it chiral, and so that's why we use it. Industry is getting more and more into using enzymes, but enzymes have a lot of drawbacks. What you learn in biochemistry about enzymes is only partially true. From the biological perspective that they're teaching it to you, it's absolutely true. When you remove an enzyme out of its biological environment, it behaves differently. Okay? Enzymes typically need to be in an aqueous environment. Organic chemists typically need to be in an organic environment, right? A lot of these types of molecules are not very soluble in water. So it would be very difficult to have an enzyme that would work on them. It just so happens that the enzyme that I use, pig liver esterase, can work both in organic media and aqueous media. And so it turns out to be pretty nice. A lot of enzymes are extraordinarily expensive. So there's nothing, it's not uncommon when you're in a biochem lab to buy a little vial of an enzyme that when you open it up, you're like, is there anything in there? And that cost $1,000. Okay? Now imagine trying to scale that up to making tons of a molecule. It becomes impractical. However, this is a natural amino acid called proline. You can buy it by the kilogram for pennies on the gram when you buy it in bulk. It's a lot cheaper. And so using smaller molecules usually has a cost advantage over large macromolecules.
So what was the process in which they found that catalyst? Do they
So what was the
other ones that they test before they found what exactly were they looking for?
So you're actually you're starting to talk about the scientific method, right? And we'll have a session on the scientific method later in the semester. But organic chemists have been interested in a long time in how to put molecules together. And if I remember correctly, Dr. List found a paper from way back when, I think in the early 1970s, where somebody had shown that you could use something like proline to catalyze a reaction. So we keep using this word catalyst. You all know what a catalyst is? What is a catalyst?
It lowers the activation energy.
Okay, so we know that reactions don't just happen, right? They have to go through some type of energy transformation. Somebody talked about thermochemistry today that's going to be on your exam. Probably talked a little bit about energies, right, of different things. So right, a catalyst will lower the activation energy of that reaction, which makes the reaction do what? Speed up. That's right. If you think about the reactions that are responsible for my hands moving right now, if there were not catalysts, I would be moving extremely slowly.
Like a sloth.
Like a sloth. That's right. Well,
Do
probably.
they not have catalysts?
No, they do, but they're just a slower animal. So it allows the reactions to speed up. What else do we know about catalysts? Lowers the activation energy. We've got that. What else about them?
They don't affect the resulting, they don't affect what,
The product.
yeah.
They don't change the equilibrium, right? Or product and reactant. I think that's where you're getting at. They're not consumed in the reaction. That's the key thing here, right? So if I'm a company Do I want to use something that gets used up in the reaction to make it happen, or do I want to use a catalyst? I want to use a catalyst.
Something that's not
Right.
part of the product.
That's right. I want to use a catalyst. So really, I might be using, as examples, I might be using 100 milliliters of this molecule, which is acetone. It's fingernail polish remover, okay? I might be using 10 or 15 grams of this molecule, which is just what's called an aldehyde. Don't worry about that. It's a functional group, but it's cheap. And I may be only using milligrams of this catalyst to make the reaction go. I just need a little bit on the end of a spatula to make the reaction go. Okay? So that catalyst lowers the activation energy, allows the reaction to occur, because when I put these two things together, the reaction should happen, right? And it does. But I can go and monitor that reaction on the first day that I put those two molecules together, and I will just see pure acetone and pure aldehyde. I can come back a year later and I will see almost pure acetone and pure aldehyde just sitting with each other. I could come back in 100 years and I might just start to detect a little bit of the product. That's impractical. But I throw a little bit of the catalyst in, and in 15 minutes this reaction's over. It speeds it up that much. Okay? So not only does it speed up the reaction, but because it has handedness, it controls how those atoms are arranged in space, and it controls the outcome of the reaction stereochemically, which is very, very important. Okay. So I hope you understand a little bit more about why this whole concept of chirality, which you'll learn about in organic chemistry, which will be important for you when you get to biochemistry, is important, and why these two individuals deserved to be recognized with the Nobel Prize. Okay? This is work that has resulted in the manufacture of drugs that you all use. Well, you all may not, I hope you're not on any of these drugs, but there are a lot of drugs out there that are made using organocatalysis these days, small molecules to catalyze the reaction. All right, with that, I'm going to give you 10 minutes back of your life, and I will see you all next week.